All right. So in this video, we're going to walk through the solution of part 1 and part 2 of module 3 that focuses on the uncertainty quantification in nonlinear static analysis of structures using quoFEM and OpenC's Tickle implementation. So let's start first by kind of walking through the entire module, kind of what are the different questions that we have there and what are the activities we need to do. And then we're going to look at the input files that we have for this module, the starter code, and start working through part 1 and part 2. And with that, then students will have the opportunity to solve on their own part 3, and we will be doing some descriptions here and giving some hints into what would be a good way to address and solve efficiently that part 3. So module 3, the activity description, basically, we start with one building, right? And we are going to focus here on one building. This is a 4-story special steel moment frame building that's located in a high seismic hazard region. And what we want to do here is to evaluate the seismic performance of this frame following the ASCE 41 provisions using a static nonlinear procedure with, of course, second order inelastic analysis or pushover analysis. This is kind of the plan view of the frame, and this is the elevation of the frame that has reduced beam section connections, RBS connections, and kind of is the one that you can see on the lower part of the plan view. That frame, that perimeter frame that has moment resistant connections with the RBS detail to ensure kind of nonlinear response in the beams rather than the columns. It's idealized with a 2D OpenC's model in Tickle. The main script of that model is already provided in the starter code, is the one that has this name, and we will look at it in a second. But basically, kind of is described in this figure, right? Where you have all the nodes sort of number here in black, and those are the nodes that kind of denote that control each of those grid corners where the beams join the connections. We also have a truss element here that connects to a leaning column that provides the kind of the effects of the mass of the gravity system corresponding to this frame that's responsible for taking the lateral forces. The first step in the analysis is really just completing the relevant parts of the OpenC's model in the Tickle again that we have. And to do that, we are going to use we're going to first construct the DBE spectrum per the ASCE 7 and calculate the design base shear that this frame would have. We already have an estimation of the period. The first mount period of the building calculated with OpenC's is 1.12 seconds. So we will use that period then to estimate what's the design base shear. And of course, remember that the DBE is 2/3 of the MCE, and at this side, the MCE ordinates are 1.5 G for SS and 0.6 G for S1. This building is a special steel moment frame, has an R factor of 8. Then we will calculate the specified roof target displacement following the equations from ASCE 41. So you can look at that, and we will have some, we will assume the coefficients C0, C1, C2, as is kind of mentioned here. It's really important that you can read through ASCE 41 and kind of familiarize yourself into what are those coefficients kind of mean and what they try to capture, which is kind of out of the scope of this module and this video. Then you set the maximum roof displacement of the pushover analysis in the set solver Tickle file. We looked at it again. We will look at it after we finish looking at the module prompt as basically 1.2 times the one for the MCE target displacement, so that we can kind of really capture the full pushover curve. And then we'll complete the lateral load pattern analysis, the lateral load pattern file, also adding the force distribution following ASCE 41. That would be part 1. So basically, mostly hand calculations and looking at ASCE 41 and completing the OpenC's Tickle implementation in the parts that are described here. Then we'll calculate the nominal pushover curve of the frame using quoFEM, right? So what we want to do is then we're going to take that model in Tickle and the solver script also in Tickle, and we're going to put it in quoFEM and perform really a one-time analysis. And the way we'll do that is with forward propagation with just one sample, right? So we're going to do it only once first, following the steps that are described here. And this part I will skip, and then when we start solving it, we looked at them a little bit more in detail. And the idea here is that we will get a pushover curve, just one pushover curve, and we will compare it with, you know, the assumptions from the design, the DBE, and the MCR targets. Then we will, then part 3, which we will not kind of solve here. Instead of doing just one pushover analysis, we'll do multiple, right? Will be a true forward propagation where we will assume the type of distribution for a few parameters of the building, right, that describe the building behavior, right? And those are already kind of predefined in that OpenSea Stickle file, the elastic modulus of the steel material, the yielding strength of the column, and the yielding strength of the beams, right? So those, and we are going to set them as log normal with a mean and a standard deviation that increases depending of how detailed of experimental campaign are you willing to do in the building, right? So you say, I will gonna do a really detailed experimental campaign, so that way the coefficient of variation of the uncertainty in the model parameters will be relatively low. And if I do really no experimental campaign or just a really minimal one, I will have a lot of uncertainty. And then that will kind of trickle in our parameters with high coefficient of variation, and therefore we will expect to have a higher sort of uncertainty in our pushover curve. But here we'll be able to repeat that analysis, do it multiple times, and see how the pushover curves compare to each other, and how that uncertainty increases and how it compares the full sort of realizations of pushovers with the nominal that we assume without, you know, ignoring uncertainty. And that will kind of give us some sense of how important is this uncertainty and how much our response can change just given the uncertainty that we have. So let's start with looking at the starter code first, which is important for the first part of the problem. So looking at the starter code, here we have module 4 starter code frame model. And inside frame model, you see the two files, a solver and a model. So let's look at that. So if we open up here, okay, so we have here our OpenSea model open. There we go. So this is one of the input files. So you have two input files, the OpenSea model itself, the 4-story concentrated plasticity frame model, and then the solver pushover, which is the script that will take that model and would apply a displacement control analysis to solve the pushover, to give you the pushover curve. So how does this work? Basically, we can walk through it. This is OpenSea's Tickle implementation, which is basically another way that you can use OpenSea beyond the OpenSea PY, that uses just a little bit of a different interpreter, but in concept you do the same, right? You always start wiping the model, so clearing the memory. You define the model, say it's a 2-dimensional 3 degree of freedom model. Here you can, for example, create some functions, which in Tickle language, instead of doing def and then the name of the file or the subroutine, you use proc, like procedure. And then you continue doing, you define some constants in the model, create the nodes. So you create all of the nodes, then assign some constraints, equal degree of freedom constraints, boundary conditions, then define section properties and elements. So here you'll create like material models if you need to, then create elements, in this case, elastic beam columns, then define rotational springs. So here is where you create rotational springs, in this case, using the IMK model You can read a lot more about this on the OpenSea's documentation. So you create all of the nonlinear springs this way. There's one way you can do it. And then apply the gravity load. So here you're applying the gravity load, and then do an eigenvalue analysis to get the period. Now you can take that model, source it on your solver, and then basically kind of start with this script finishes, and then define your pushover analysis. The way you will define a pushover analysis in OpenSeas is that you need to define first what are the control nodes of the building. So what are the nodes on, well, like with a node you're going to apply the force, and then you're going to focus on for each of the floors. So there will be node 31, 32, 33, 34, 35. You can feel free to go back and look at your the model description, and in figure 3 you will see that the middle column, it's the one that has those nodes, right? Here on figure 3, 31, 32, 33, 34, 35, those are the nodes that that we are using as the controlling nodes for each of the stories or each of the floors of the building in our analysis. If we go back here, then we define that we have 4 stories, and we're going to apply all our nodes, or the control node that we are focused on is the node on the roof. So basically the way pushover analysis work is that you choose one node, and that's the node you're going to push and control the displacement. And so you want to say, I want to push this node to the right or to the left, all the way down until you get to a maximum value of displacement. And you need to say in which degree of freedom you want to move that node. So typically you would do a horizontal degree of freedom, so 1. And then here you need to say what's the target displacement, right? So we're going to do it for the roof. So here you need to define what's the maximum roof displacement. That's the result of part 1. When you do the MCER calculation, 1.2 times the MCER as defined in the module prompt. And what's the increment displacement, because all of this pushover analysis is done step by step. So we will do it in increments of 0.01. So basically we're going to chop that maximum displacement in 100 pieces and do it, 1% at a time. And then we also need to define the lateral load pattern, which is basically the one that will tell us, okay, with which force I want to push this building to follow that displacement target that you want on the roof. So here, basically, we're going to follow the equivalent lateral load equations in ASCE 7 and apply those here to make sure we are pushing the building following the ELF calculation or the ELF shape. Then here, the rest of the code here is just defining the outputs. We want to get the output, the base shear. We want also the output of the drift of each of the stories, and perform the pushover analysis. The way the pushover analysis work is that it's doing really multiple displacement control analysis. And you can walk through this code in more detail, but basically it's doing just each of those 100 analysis step by step, using some of the solver inputs that we have defined here, with number of iterations and tolerances and type of convergence tests that we have chosen that work for this problem. Here you will see that we have some loops, some while loops, and some if statements that would help us overcome convergence issues, right? In case that the analysis for some reason doesn't find convergence, in this way, it will try different methods to get past over the numerical challenges of that particular time step and continue to the next. And then at the end, it will give us the outputs of the result in text files, where we basically will get one text file for the base shear and another set of text files for the drift response on each of the stories. All right, so now that we understand and kind of know how those inputs are, let's start solving the problem. So if we come back here or to our module prompt, and let me share it here 1 second. So we got our module prompt here. The first part is just basically hand calculations that we have kind of I have pre-done here for the sake of time. So we can you can go back to your notes, review ASCE 7 and ASCE 41 to estimate first the MC design spectra and the target displacement from ASCE 41 using the coefficient equations. So you can look at the answer sheet here on the right here. Here we go. You should be able, let me make sure you're seeing the right file. There we go. So here you see the answer sheet for this module 3, where you can then with the a spreadsheet or something follow the equations in the building code to get the spectral acceleration, the design spectrum, period, and pseudo acceleration for the S1 and SS that we have provided in the module prompt. Then you can enter here with 1.12 seconds, which is the period, the fundamental period of this building, obtain what's the pseudo-spectral acceleration multiplied by the weight of the building and divide by the R factor to get the design, the elastic design for, I mean, the inelastic design force, which in this case would be 408 kips. Now, the part B here is just using the equations from ASCE 41 for DBE and MCE. Those equations is basically the coefficient method in ASCE 41, when you have a series of coefficients that we have provided in the module prompt, multiplied by the value of SA, the pseudo acceleration for the fundamental period of the building, kind of turn from pseudo acceleration to displacement. And then for DBE is multiplied by 2/3, and for MCE, it's directly the value of the design spectrum. And that will give you 8.5 inches for the DBE and 12.8 inches for the MCER. What this means is that the target displacement, the roof displacement of this frame would be 12.8 inches, expected to be 12.8 inches for the MCER event, or 8.5 for the DBE event. That's what we would kind of expect based on the ASCE 41 equations, the top of the building to move. And then we estimate the lateral load pattern from the ASCE 41 equations, equivalent lateral load pattern, and follow those equations, and then you get those coefficients applied to the lateral force. So what we do here is that we go back to that script from the pushover in the starter code and replace those results there. So let's go back and look at how it looks like once we have replaced the results we just computed. So let me open it up. So when you open up the solver pushover, this is what you will see. There you go. So this is the solver pushover. So when you open it up, you basically need to define here, you'll see the lateral load pattern, which is the one we just calculated here, right? For floor 1, floor 2, floor 3, and floor 4. Those are the ones that you kind of place there from the solution of the part 1C. Up here for the MCE, you need to define 1.2 times the MCER roof displacement. The calculation gave us 12.8 inches for the roof displacement for the MCER, multiplied by 1.2. Notice how in Tickle language, whenever you do like a mathematical operation, you need to place that into brackets and put the EXPR, like expression, before that, so that the interpreter would understand that what you're doing is really an operation between this number and this number, like this float and this float. Basically, that's it. We now have defined the maximum displacement target, and we have defined the lateral load pattern here. We have everything we need now to do the pushover analysis. So now the next step is to go to quoFEM. So let's go to quoFEM and see how we can do this nominal pushover analysis. So let's stop sharing here. Okay, so now we're gonna open quoFEM. We're gonna do part 2. So we go here, let's look at quoFEM. So we have opened quoFEM, run as administrator, And we're going to run it then following those steps that are in the second part of the module, right? Which basically prompt us to do a forward propagation, which is one sample, because we don't really want to do a forward propagation. We just want to run it once, but use quoFEM as our way to kind of manage the model. We are going to define in the finite element model OpenSees, because this is an OpenSees Tickle implementation. We're going to assign then here the model. So we're going to go here and then say we're going to put the model. So the Tickle model, you look for in your files for the in class in this case, but then when you're solving the homework, part 3, you would choose the one that's on the starter code folder. Then here we're going to use the post-processing script, because we have a different file, the solver pushover .tcl file, that it's the one that is going to take the model, the input script, and solve it, right? That's the one that has all of those, you know, all the parameters to solve the pushover. So we're going to use it here. And that's the one we're going to define in the post-processing script. Now, in the random variable case, automatically the model or the quoFEM, after kind of looking inside the OpenSees model, would identify that some variables were defined using the pset approach instead of the set approach. So let's actually go look at OpenSees model to clarify what I mean with that. So if you go and open the OpenSees with your text file of text reader of preference, you will find this. And you see the model, and you see that any sort of definition of any parameter, any variable in Tickle language uses the command set, right? So for example, here what we're saying is we are saying the variable number of stories is set to a value of 4. The variable nbase is set to a value of 4 also. The variable wbay is set to a value that corresponds to 30 multiplied by 12. So 30 feet, right? 30 by 12 inches. And then also here, every time you kind of define a value in Tickle language, you do a multiplication or a division or any kind of parameter or float operation, you need to do it this way, right? With brackets and putting the expression symbol behind. So that's what we're doing. There is a special type of set that's called pset, and let's look for it. Pset, right? And then pset, what it means is that we are setting a probabilistic variable, right? So basically saying this variable es has this initial value, but it's probabilistic, so it's a random variable. And that's what quoFEM goes and looks for in the OpenSees file, and identifies all of the variables that have that pset that were defined using the pset, and assumes a distribution, normally, usually a normal distribution, assign that value that we put there as the mean and a standard deviation. Since we're doing basically just one run with a really low standard deviation, we can use a really low value that, given the range of numbers that we have on the mean, a value of 1 is really small. Then we define the EDP, the quantity of interest. We will use drift of the quantity of interest, and the length of that drift is 3, because the output in OpenSees for envelope parameters like drift is usually 3 numbers, right? The minimum value with the corresponding sign, the maximum value with the corresponding sign would be positive, and then the maximum absolute value of those two. So always a 3-size vector. And then with that, we are ready to run the analysis. We run the analysis, it says that the analysis is complete, but we don't have really any output to look at, right? So the way we kind of go about that, well, we have just a little bit of output, which is for that one run, what's the mean value of the drift that we got, of the minimum, the maximum, and the maximum absolute. But that's not really the pushover curve, which is what we're interested in. To look at the pushover curve, we need to go inside the working folders that OpenSees and the quoFEM produces to get kind of the intermediate results. So let's go do that. To do that, I will kind of recommend you to, inside quoFEM, go to Files, Preferences, and then when you're there, you will find path that says Local Directories. And let me just show you that in a second. There you go. So if you go here to File, Preferences, you find this window, this pop-up window, and you find the local jobs directory. The local jobs directory basically is the one that would be holding all of the folders or the files that quoFEM is producing on the background to then show you the results. So you can go there, you know, in your Windows Explorer, you can go there, and then you'll find this temporary Sim Center folder. You go inside there, and inside that one, you will find a working directory. That working directory is the one that holds the one run that we did here. So you can go inside there, and then you can find your model. You can find the solver script or the post-process script. And then also you can find some outputs that come from OpenSea. Specifically, you can find the base shear, the gravity, and the displacement of each of the 4 floors. So we're going to copy all of those guys, and we are going to put it in a safe place. So for example, here in class files, you know, you can go and save them somewhere. You can go and save them. Good. Now we are going to use Google Colab to post-process those results. So how do we do that? We will basically go here to our starter code, and then you can open the starter code Google Colab file. Let me now, I just open it up and I will share it here. There you go. So now we have, here is our starter code that it's basically ready to show us our results. So first thing we do here is that we kind of populate it. We started running it, accessing the virtual machine. We need to put here our results from part A, the V design, the roof displacement for DBE, and from NCER. For MCER, the roof displacement was 12.8. For DBE was, let me just double check, was 8.5. And the B design, excuse me, the B design was 406, skips 406. So we assign those. And then we need to upload the results or those text files we got from the working directory of quoFEM. And we need to upload gravity, base shear, story 1, 2, 3, 4, displacement. So we go and choose all of those. We have them here on module 3. We got base shear, we got gravity, we got story 1, we got story 2, we got story 3, story 4. There you go. Those are all the 4. Then we're basically, what that's doing, it's just putting all of those files in the environment in the virtual machine. Then we will read those files into variables on our notebook and then plot it. There we go. And then here you have the pushover curve plotted coming from the analysis you just did in quoFEM. And it's important to take a minute to kind of understand and reflect on these results that we have here. We have 2 plots, one that's showing the base shear in the vertical axis and the roof displacement in the horizontal axis. And then another one that normalizes those, right? It has the base shear coefficient in the vertical axis. So basically all the lateral force, the base shear divided by the total vertical or gravity force. So then you have a shear coefficient. And then in the horizontal axis, you have a roof drift, right? So you have the roof displacement divided by the entire height of the building. Now, what you can see here is that also you have these dotted or dashed lines that depict the base, the design base shear after it's divided by the R factor. And you can also see the DBE target and the MCE target in terms of displacement, 8.5 and 12.8 inches of roof displacement. And then you can see here how, you know, the building, the pushover curve goes way above the force design, right? Like the building was designed for these almost 400 kips of lateral force of base shear. but the building is capable of resisting a lot more, right? At least according to the nominal pushover, and that's because all of the sources of redundancy and overstrength. You can compute that overstrength and look at and how much that value would be. And here we have a summary of that. Here, of course, we need to replace this by the proper calculations to calculate the overstrength factor. So for that, we need to kind of look at, right, what is the maximum force that we see here. That value we can find that. Let's see. We need to look at what are we plotting here. So the base shear nominal, that's the maximum value. So for if we want to write here our overstrength factor, we need to put here the maximum value from NumPy of this, and then we divide that guy by or V design. Let's see, where's the design? Oh, that wasn't the name. The name of the variable was that we have defined at the very top here, V design without the underscore. So V design. So we have a calculated overstrength factor of 2.65. That's our calculated overstrength. That kind of relates the design force with the actual maximum force that we see from our pushover analysis. We can also kind of estimate or compute the drift, right? What's the drift? The roof drift ratio for the DBE, and then the roof drift ratio on the drift ratio for 4th, 3rd, 2nd, and 1st stories. So let's do that really quickly here. So let's open this up here and replace these values. So what are we talking about when we say roof drift ratio for DBE? Right, the roof drift ratio for DBE is the roof displacement for the DBE divided by the height of the building. What's the height of the building? We have defined it here with H underscore story. So that would be the roof drift ratio at the DBE. Now, how do we compute this, the drift at the 4th story? Right, the drift of the 4th story is the displacement of the 4th floor minus the displacement of the 3rd floor divided by the height of that 4th story. So what are those? Right, and that's for the DBE. So here we have searched for the displacement at each floor for the DBE. We have the displacement at the 4th floor at the DBE. We subtract from that the displacement of the 3rd floor to get the relative displacement that only corresponds to that top story, and divided by the height of the floor, which is H story. Oh, and actually we need to correct that. The roof drift should look at the drift of the entire building, so it's H, not H story. Apologies for that confusion. So let's finish up here. We divide this by the height of that 4th story only. Now coming back to the roof drift ratio, this one should be divided by the H only, right? The height of the entire building. Now we can kind of copy the same concept for floor 3 and floor 2. But now we need to adjust it, right? For the 3rd story, it's the displacement corresponding only to the 3rd story correspond to the subtraction of the total displacement on floor 3 and floor 2. And then from 2nd story is floor 2 and floor 1. The only difference for the 1st story is that it's fixed on the bottom, right? So it's only need to, the only displacement is the 1st floor displacement. So we got floor 1 divided by the H story. And that should give us the drift for each of the floors at the DBE level, right? So at the DBE, we have then at story, the drift at the 4th story is almost 1.4%, at the 3rd story is 1.8%, 1.6 in the 2nd story, and 0.8 at the 1st story. And that's how we kind of get the drifts that correspond to the roof displacement that we estimated with the coefficient equations from ASCE 41 that are this dBE, that correspond to the dBE lateral force. And that's what we are asked here in part 2. We also could kind of do the same analysis for MCE, right? We report the calculated over strength already, 2.68, and then we need to kind of write up our analysis and what do we think, how do we think that the building would behave for DBE and MCE, right? It would be instrumental also, if you like, to look at what would happen or what would be the drifts for, not for DBE, but for MCE, right? So for that, we could modify this a little bit. You know, you're welcome to then, instead of search for the floor displacements corresponding to the DBE, do it for the floor displacement corresponding to the MCE and repeat this calculation. We can do that here real quick. MCER, then that we're searching for the MCER and recalculate this, and then you see how for the MCER the drifts are a lot bigger, right? We get to 2.5%, whereas before we were at 1.8%, right? And notice how before we were in 1.8 and now we are in 2.5, and that ratio is not exactly the 2/3 that we assume from DBE to MCE in terms of force, right? We take the MCE aspect and reduce it, multiply it by 2/3, but looked at the relationship or the ratio of drifts is not 2/3. The ratio of drifts is bigger, is 0.72, which kind of speaks again to the nonlinear sort of behavior that we see in this structure and in any structure really. So now what would be remaining here and would be the opportunity of you guys sort of solving this module is to repeat this analysis, but now instead of doing just one run, do multiple runs, right? So instead of doing just one, you do 50 or actually 100 samples for forward propagation, but now assigning a log normal distribution to each of those random variables with the mean values that has been preset, but with the standard deviations that increase depending on the detail, moderately detail, or minimum experimental campaign. Run that, go look into the quoFEM temporary files, then you will have not only one working directory, but 100 working directories that have each of them of the runs for the pushover curves. You zip those files up and upload it to quoFEM. And then quoFEM will be able to, in the rest of these cells, plot the pushover curves for that case. Thank you very much, and good luck solving the module, and hope it's instructive. Bye.